Assalamualaikum and good day to Dr. Johanna and everyone. So we are from Group 9 and I am the leader for this experiment. So our group members consist of Raiden, Antasha and Pavitra. Today we are going to present about experiment 3 which is major losses in pipe. Next. So this is the contents of our presentation today and I will pass to Antasha to start our presentation.
Okay, so hello, my name is Santasha. So I will present about the summary of this experiment. Okay, so the first thing, major losses are associated with frictional energy loss that is caused by viscous effects of fluid and the roughness of pipe walls. Major losses creates a pressure drop along the pipe since it must work to overcome the frictional resistance. So by evaluating the Bernoulli's equation, there are some factors that affect the head loss in pipeline, which are the length of pipe, internal diameter of pipe, and flow rate. So, for instance, if the internal pipe diameter is double, the head loss will be reduced by half. If the flow rate is double, the head loss is increases by a factor of 4. The objective of this experiment is to determine the friction factor by measuring the pressure head difference between 2 points in a straight pipe. Different flow rates along with different diameter and roughness of pipe were introduced such as galvanized steel pipe, copper pipe, and PVC pipe. Okay, next. Okay, so from the experiment, the coefficient factor can be calculated by using some formulas such as from Moody chart, Colebrook, Blazes, and Moody formulas. We also can compare that different types of pipes will result in different measured head losses, and we can see copper pipes have the greatest number of head losses. So the Reynolds numbers was used to categorize the flow pattern between laminar and turbulent flows. In this experiment, as the F increased, the Reynolds number decreased. This shows pro- the inverse proportion between the coefficient of friction and the Reynolds number. The factor of the friction in laminar flow is the only use of Reynolds number and it was independent of the vessel surface roughness. The friction factor in totally turbulent flows relies on Reynolds number and the pipe's wall's relative roughness. So, but mostly the coefficient friction that will be calculated will be estimated based on the Moody diagram. Okay, so next.
Next, for the theory part, in hydraulic, passing a certain volume of liquid through a pipe requires certain amount of energy. Energy or pressure difference must exist to cause liquid to flow. A portion of energy is lost to overcome the resistance to the flow. At the same time, other factors such as change in velocity and elevation also lead to energy dissipation. This dissipation of energy leads to energy loss, which technically defines as heat loss. By applying the energy equation to a section of a straight pipe with same diameter, the energy loss in a pipe can be determined as the following equation. If the pipe is horizontal, thus Z in equals to Z out. Since V in equals to V out, the equation will be HL equals to pressure out minus pressure in over Y. Based on equation 2, the head loss is directly proportional to the pressure difference. The head loss will increase when pressure difference increase. The pressure difference between 2 points in the pipe is also due to the frictional resistance. Friction losses in pipe are termed as major losses, which can be calculated by Darcy-Weisbach formula, the formulas, where P is pressure loss, rho is density of flowing fluid, HL is head loss due to flow resistance, F is Darcy-Weisbach coefficient, L is pipe length, di is pipe diameter, V is average velocity, and G is gravitational acceleration. Next slide. Table below shows the kinematic viscosity for water at different temperature. Reynolds number of the flow will normally be used to determine whether the flow is laminar or turbulent. Reynolds number is given by as follow, where Re is the Reynolds number, V is the pipe velocity, D is the pipe diameter, V is the kinematic viscosity. However, next slide. However, in a fully turbulent flow, F can be determined by using a Moody's diagram. This is Moody's diagram. The friction factor can be determined by applying empirical formula instead of using Moody's diagram. The friction factor for turbulent flow in a smooth pipe is valid for a Reynolds number less than 10 power 5. Can be obtained by using the Belcher's formula as below. Then, for the Colebrook formula and Moody's formula, F can be calculated as the following equations. Next, I pass to Nafisha.
Now I'm going to continue with the apparatus for this experiment. So the apparatus used to carry out the experiment is a pressure measurement test bench, which consists of rotameter, thermometer, gate valve, feeding hose, measuring sections, 2 tube manometer, 6 tube manometer, differential pressure sensor, meter display operator, pump switch, cover switch, electronic pressure sensor, return hose, return valve, interchangeable measurement graph, and also pump. I will explain about the procedure of this experiment. First of all, both feeding and return hose are connected to the tested pipe section. Next, the manometer tubes at one of the two tube manometer, which is the H1 inlet and H2 outlet, are connected to the tested pipe section. Third, the main switch and the pump are turned on. The gate valve are open slowly until the reading of rotameter or the actual flow rate reach 2 meter cubic per hour. Step 5. The ventilation valve, which is the black one on top of the 2 tube manometer, is opened by turning it into anti-clockwise direction to let the water overflow from the system and release all the bubbles if have in the system. Next, the ventilation valve is closed back by turning it to clockwise direction when there is no bubbles present. Next, the gate valve is closed and the pump are turned off. Next slide. For step 7, the ventilation valve, the white one on top of the 2 tube manometer is slowly open until the preset minimum reading of the 2 tube manometer reach 25 millimeters for galvanized steel and PVC pipes, while 1 millimeter for copper, PVC 20 and PVC 32 pipes. After that, the gate valve is opened slowly until the level of water at 2 tube manometer of H1 reach the maximum while H2 at the minimum. The two tube manometer reading H1 and H2, the temperature, the Q actual are recorded. Next, the Q actual is reduced to 5 different values by adjusting or reducing the opening of the gate valve. The minimum value of Q actual should be around 0.2 meter cubic per hour. So all the reading H1 and H2, the temperature and the Q actual are recorded. Step 10. The manometer tubes at the two tube manometer are transferred to the differential pressure sensor where P1 inlet and P2 outlet. The bubbles are ensured to be not present in the system by opening the ventilation valve at the differential pressure sensor prior to record the reading of the differential pressure sensor at the digital display for pressure for 5 different values of Q actual. So next, the ventilation valve is closed if there is no bubbles present and the QX, the temperature, the differential pressure reading are recorded. Next, all the manometer tubes are removed from the system. The gate valve is closed and the pump is turned off. Lastly, the feeding and the return hose are changed to another pipe section. Steps 1 to 11 are repeated for different types of pipes. So that's all for me. I will pass to the next presenter to continue our presentation.
Hi, I'm Redan and I will continue with the result part. So this is our results. For the experiment, we used 5 types of pipe, which is galvanized steel pipe, copper pipe, and 3 PVC pipe with different diameters. So for galvanized pipe, we use 6 flow rates, and we recorded the H1 and H2. H1 is the maximum height of flow meter, and H2 is the minimum height of flow meter, and we find the difference in H, and we recorded it. And same step is used for copper pipe, PVC pipe, and also PVC pipe with 3 different diameters. So next, we'll continue with the discussion part. So this is the comparison between the coefficient of friction for each of the tested pipes in the experiment with the coefficient of friction from Moody chart and calculation using a formula of Blasius, Colebrook and Moody. So this is the sample calculation for galvanized steel pipe. Uh, the diameter for galvanized steel pipe is 0.0127 meters. The relative roughness is equals to 1.5 times 10 to the power of negative 4 meter. And the division between relative roughness and diameter gives us 0.01181 meters. So we took the average flow rate from the data we got and we use it for the calculation, which is 0.45 meter cube per second. And we found the velocity. The formula will be 4 times flow rate over pi times diameter square. And we got the answer 0.9868 meter per second. To find the kinematic viscosity, we use the interpolation method to find the kinematic viscosity at 31.5 degrees Celsius. So from that, we got the kinematic viscosity is equals to 7.7947 times 10 to the power of 97 meter cube per second. And from there, we found the relative Reynolds numbers, which is the formula will be velocity times diameter over kinematic viscosity, and we got the answer 16,078.053. So using this Reynolds number, we can find the coefficient of friction. So from Moody's chart, we got the coefficient of friction is 0.042, and from Colebrook formula, which is the formula is 0.01 0.001375 times with the 1 plus 200 over 200 times with the relative roughness of diameter plus with the 10 to the power of 6 over Reynolds number, and it is powered with 1 over 3, which we got the answer is 0.0432. And for Blasius formula, which is the formula is 0.316 over Reynolds number powered with 1 over 4, which we got 0.0281. And for the Moody's formula, which is 1 over square root of friction, coefficient of friction, which is equals to negative 2 log bracket relative roughness over diameter over 3.7 plus 2.51 over Reynolds number times with coefficient of friction square root, which we got 0.0055. And for other pipes, we use the same method of calculation to calculate the coefficient of factor. So from the calculation for copper pipe, the coefficient of friction from Moody chart will be 0.021. Uh, Using the Colebrook formula, the coefficient will be 0.0213. Using the Blasius formula will be 0.0212. And for Moody's formula is 0.00381. For PVC pipe with the 20 millimeter times 1.5 millimeter length, we got the F value from Moody chart will be 0.022. Colebrook formula will give us 0.0219 and Blasius formula gave us 0.022 and Moody's formula gave us 0.00398. For PVC pipe with 32 times 1.9 millimeter length, the coefficient of friction gave us from Moody's chart we get 0.022. From Colebrook formula we got 0.0218. From Blasius formula we got 0.0219, and from Moody's formula we got 0.00398. And last one, PVC pipe with 16 times 1.8 millimeter length. The from Moody's chart we got 0.026. From Colebrook formula we got 0.027. From Blasius formula we got 0.0274, and from Moody's formula we got 0.00532. So these are the possible reasons for the difference in their values. The values of F that obtained from the Moody's chart for all types of pipe are the same as when calculated by using the formula of Blasius and Colebrook, except for the galvanized steel pipe. There is a slightly different when using the Moody's formula. This is because Moody's stated that the accuracy is about approximately 5% for smooth pipes and 10% for rough pipes. For galvanized steel pipe, the value that obtained from the Moody's chart and Colebrook's formula are the same, but there's a huge difference when using the formula of Blasius and Moody. This is due to the process of calculation of Colebrook's formula, which more details as compared to the Blasius formula that only required few parameters in the calculation. While the difference of the values obtained from Moody's chart and Moody's formula is because same like before, Moody stated that the accuracy is about approximately 5% for smooth pipes and 10% for rough pipes. Next, this is the rankings of pipe in ascending trend based on their major head loss value obtained from the experiment. So the equation we use is HL. The formula for HL is F, which is the coefficient of friction, times with the length over diameter, and times with the kinematic viscosity square divided by 2 times gravity. So based on the calculation, the lowest major head loss is the PVC pipe, 32 millimeter times 1.9 millimeter, which is 0.049, and this is followed by PVC pipe with a 16 millimeter times 1.8 millimeter length, which is a 0.115 meter in the major head loss value. The third pipe will be galvanized steel pipe, which is 0.164 meter in the major head loss value, and the fourth pipe is PVC pipe with 20 millimeter times 1.5 millimeter length, which has the major head loss value about 0.167 meter. And the last one, the highest major head loss is the copper pipe, which is 0.369 meter. Calculation, we can rank in ascending trend as shown. The lowest major head loss, PVC pipe, 32 millimeter times 1.9 millimeter, because it has the largest diameter of pipe and has the lowest absolute roughness, which is negligible. It happens because when the diameter of the pipe increases, the flow area increases, and then the velocity of the liquid at a given flow rate is reduced. When the velocity is reduced, there's the lowest major head loss due to the friction in the pipe. Besides that, when the roughness of in the inside pipe wall decreases, the thickness of the slow or non-moving boundary layer of liquid decreases. This will result the increase in flow area and the reduce in the velocity of the liquid. Thus, it decreases the major head loss due to the friction. Referring to Darcy-Weisbach equation, when the inside pipe diameter is double, the head loss will be reduced by half. However, it increases with the increasing of volumetric flow rate. Hence, when the flow rate increases, the major head loss increase at the same time. So the ascending order will be PVC pipe 32 millimeter times 1.9 millimeter length. The second one will be PVC pipe 60 millimeter times 1.8 millimeter pipe. Third one will be galvanized steel pipe. Fourth one will be PVC pipe with 20 millimeter times 1.5 millimeter length, and the last one will be copper pipe. For the next pipe, I leave it to Antasha.
One, there are I will explain about the factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. So there are multiple common sources of errors in the experiment that can cause inaccuracies in the data provided. So firstly, the environmental factors due to the working environment such as vibration, changes in temperature or electronic noise can affect the measurement. Other than that, parallax error also might occur due to the position of the eyes not perpendicular to the scale of flow measurements. Next, the presence of air bubbles in the tube, which indicated the value in the manometer, and leakage of fluid also might have occurred. Due to the rubber tube not firmly connected to the inlet and outlet valve can further contribute to error. Okay, so last but not least, an improper interpolation between lines and points while reading the Moody chart also can affect the calculations. Okay, next. Next slides. Okay, so these are the some possible recommendations that we can do to improve the results. So to make sure that the experiment is in the to make sure that we can get accurate data. So the first one is we have to make sure that the environment is in safe condition and under control to avoid any systematic error data, especially the changes in external conditions such as pressure and temperature. Then we have to ensure that the position of our eyes must be perpendicular to the scale of the manometer to avoid the parallax error. We have to keep observing that there is no presence of air bubble. So then to avoid the leakage, we have to make sure that the connection of the rubber tube is tight enough by confirming that flow rate in the pipe is the same as the flow rate in the water meter. Then, by using an updated and precise measuring device that does not have any defects, we can reduce the systematic measurement error. And last but not least, we have to be aware of the logarithmic nature of the axis levels value by calculating the graph and while taking the data in the Moody chart. Okay, next I will pass to Nafisha.
For the conclusion, the performance of the flow in pipe system is affected by the major head losses of the pipe due to the effect of the fluid's viscosity near the surface of the pipe. Major losses which are associated with the frictional energy loss per length of pipe depends on the flow velocity, pipe length, pipe diameter and a friction factor based on the roughness of the pipe and whether the flow is in lamina or turbulent. So based on this experiment, we have achieved the objective which is to determine the pipe friction factors for different types of pipes with different diameters and thickness. We also have calculated the friction factors using several different ways which is using formula of Blasius, Colebrook and Moody chart and we compared the values obtained from the calculation with the values obtained directly from Moody chart. There are slightly different in values of friction factor obtained from the calculation using different formulas. So from the result obtained, the pipe that have the largest head loss is copper pipe. In fact, the smaller the diameter of pipe, the higher the head loss. The smoother the inner surface of pipe, the lower the head loss. The higher the flow rate of water, the higher the head loss due to friction factor. So next for turbulent flow in pipe, the major head loss in pipe is directly proportional to the length of pipe, roughness of pipe, and the square of flow velocity. However, the major head loss was inversely proportional to the diameter of pipe. So that's all from us for this experiment. Thank you.